In this lecture, we're going to discuss the phenomenon of quantum entanglement. Quantum entanglement is what gives power to quantum computing, and quantum computing will not be possible without entanglement. We begin with the definition of a tensor product. So, definition. So let V be a vector space with bases V1 through Vk, and U be a vector space with bases U1 through Un. A tensor product U tensor with V is a vector space with bases UI tensor Vj, where I goes from 1 to n and j goes from 1 to k. Now, so here, this symbol here can be, for now, just treated as a purely notational thing. So it's sort of a glue that binds together UI and Vj. So equally, we could have denoted this as Wij. Right? And so what is important for us, so we see immediately from this definition that dimension of the tensor product U tensor V is equal to the product of dimensions. So it's dimension of U times dimension of V. So really, in this definition, there is no need to say that these vector spaces are finite dimensional. And so it's just, we could say that VI's are a basis of V and UJ's are a basis of U, and then this UI tensor VJ's will be a basis of the tensor product. So this definition is applicable in infinite dimensional setup as well. However, for this course, we will only need to consider tensor product of finite dimensional spaces. Now, once we defined the tensor product space, we also get the operation of a tensor product. So this will be the product operation. So this means that it operates on pairs. So if we have a vector from U and a vector from V, then it sends this pair to the tensor product space. Right? And so this is so the pair, so we say UI Vj will go to UI tensor Vj. And so this motivates our notation here. And this operation is bilinear. So this means that if we multiply sums or linear combinations, so suppose we have, instead of just UI, suppose we have a sum, I goes from 1 to n, Ci UI. Right? So this is a general vector from space U. And we take the tensor product with the sum j goes from 1 to n to k, dj vj. Right? So then the tensor product of these vectors is defined by bilinearity. So it's going to be the double sum I goes from 1 to n and j goes from 1 to k, Ci dj times UI tensor Vj. And so in this way, So we can define tensor products of arbitrary vectors from u and v. Tensor product construction allows us to put two quantum systems together. So if we have two quantum systems, so if we have two quantum systems with spaces of states u and v, then their joint space of states. So this means that now we want to consider these two systems simultaneously, so as one system. So this will become two parts of one quantum system. Then this larger quantum system will have the space of states, which is the tensor product of u with v. Right. And so we have a Hermitian scalar product on the nu. So if we have u1 tensor with v1, and we take the Hermitian scalar product of u2 tensor with v2, then this is just the product of u1 with u2, right? So this is in the space u times v1 with v2. So this is this Hermitian scalar product is taken in the space V. Tensor products also allow us to construct n-qubits. So we start with a quantum bit space. So this is space B, is really C2. It's a two-dimensional space over complex numbers with bases. So we have 0 bit and a 1 bit. And then what's a 2-qubit? So 2-qubit will be B tensor with B. Right? And so this will have bases. So 0 tensor 0, 0 tensor 1, 1 tensor 0, and 1 tensor 1. And likewise, so we can define n-qubit as iterated tensor product. So we take n copies of a quantum bit space and take the tensor product of these. And so here, so the basis of this will be the tensor product. So 0 tensor 0 tensor dot 0. So the next one will be 0 tensor 0 tensor, and the last factor will be 1, and all the way up to the term where we have tensor product of n ones. So, of course, we're going to use shorthand notations for this. So this will be just denoted as 0, 0, 0, and this one will be 0, 0, 0, 1, and this one will be 1, 1, 1, 1, right? So like here, so for 2-qubit, so the basis will be also written 0, 0, 0, 1, 1, 0, and 1, 1. Now, from our dimension formula, we see that this space has dimension 2 to the power n, right? And this is a very powerful fact, because what it represents, this represents an ensemble of n particles, right? So, for example, this can be n electrons with their spin states. And what we see is that if we have n particles, and each particle has a two-dimensional space of states, then these n particles together will have a space of states of dimension 2 to the power n. And this is huge. So this is what creates huge capacity for quantum memory. So this means that we can store tons of information in n particles, so because the information capacity behaves exponentially here. So let's look at an example. Suppose we have two non-interacting particles. With states say psi1 is equal to a times 0 plus b times 1, and psi2 being c times 0 plus d times 1. And both vectors have norm 1. So then the joint state so if we consider these two particles together as parts of one single quantum system. So this will be psi1 tensor with psi2. Now let's write it in a basis. So it's the product. So A0 plus B1 tensor with C0 plus D1. And so now this equals, so if we expand this, so this becomes AC. And now I'm going to drop the tensor product sign. So I'll write 0, 0 plus AD 0, 1 plus BC 1, 0 and plus BD 1, 1. Now, let us ask the following natural question. So, can an arbitrary two-qubit state be factored as, say, psi1 tensor psi2? Right? So if we have a state, say, Z1 times 0, 0 plus Z2 times 0, 1 plus Z3 times 1, 0 plus Z4 times 1, 1, right? So can we find two one-qubit states, psi1 and psi2, so that this becomes psi1 tensor psi2? And it turns out that the answer to this question is negative. So the answer is no. So because what we can see, so well, if it can be factored, then it can be written in this way. And so the consequence of this, so we can see that so if it can be factored, then so what we see is that the product of these two coefficients, So this is going to be, so Z2 times Z3 must be equal to Z1 times Z4, right? So because both products are going to be A, B, C, D. And so this means that if this condition fails, then this factoring is impossible. As an example, let us take a look at the following state. So let's take 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. Well, we use this coefficient so that norm of psi is equal to 1, right? And so here, so what we see is, in this case, so the Z1 times Z4 is equal to 1/2, and Z2 times Z3 is equal to 0. So this tells us that this state cannot be factored. As so psi1 tensor with psi2. So now we can give the definition of quantum entanglement. So suppose a quantum system consists of two parts. With spaces of states U and V. So a joint state phi in U tensor V is called entangled if it cannot be factored as a tensor product of two states where psi1 is in U and psi2 is in V. Right. So in particular, so this state here, so this 2-qubit is entangled because we cannot factor this as a product of two 1-qubits. Now, from the physics interpretation, so unentangled states represent non-interacting particles. And so this means that we just take two non-interacting particles and consider their joint state. And the entangled states, so this means that these two particles are involved in a non-trivial interaction. It's important to understand the relation between entanglement and observations. So imagine the following experiment. So suppose we have a source that produces a pair of entangled particles, right? And so we have two, say, polarized photons, and one photon is sent to the right and another is sent to the left. And here we have two detectors. So here we have kind of a detector A. So this is Alice is going to observe this photon, and here we have a detector B so with Bob going to make observations on the photon that goes in this direction. And so imagine that the joint state that we generate is that one. So 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. So what will happen with observations of Alice and Bob? Now, let's assume that Alice makes her observation first. So observations of Alice. So if we're given this state, and so what we're doing is we're measuring the value of the first bit of this state. So Alice can observe the value of the first bit to be 0 or 1. And so this will happen with probability 50% each. So with probability 50%, Alice will observe 0, and with probability 50%, Alice will observe 1. But we know that observation changes the quantum state. So this means that when Alice makes her observation, so the state will collapse. So where will it collapse to? So here we see that if Alice observes 0, then the state will collapse to renormalized state corresponding to the first part. So this means that so the new state becomes here just 0, 0. Right? So if Alice observes 0, then the state projects to this state. And if Alice observes 1, then the quantum state will collapse to 1, 1. And then now imagine that Bob makes a measurement, right? So Bob's observations. So what we have is that, again, with probability 50%, Bob is observing, so 0 with probability 50%, and 1 also with probability 50%. But what will happen is there is a correlation between observations of Alice and Bob. So this means that either both observe 0, 0, right? Or both observe 1. So in this experiment, it is not possible for Alice to observe one value and for Bob to observe a different value. So this means that with probability 50%, each observes either 0 or 1, but there is a perfect correlation between their observations. So if Alice observes 0, then the quantum state will collapse to 0, 0, and then Bob has to observe 0 as well. If Alice observes 1, then the state will collapse to 1, 1, and Bob will observe 1 as well. In order to understand what's going on here, so let us recall what is conditional probability. Suppose we have two events, A and B. And let's draw a Venn diagram here. So we have, one event is A, and another event is B. Right? And here we have intersection of these two events. So this means that this is, here we have A and B simultaneously. Now, so what is the conditional probability of A under the condition that B happens? So here what we do is instead of looking at the whole space of possibilities, we only look at the part where B happens, right? So we kind of restrict our space here. And there, so we want to consider all cases, so assuming that B happens, but also we want to see what's the probability that A happens, provided that we only consider the cases where B happens. So this means that we limit our universe to just event B. And then, so from this Venn diagram, we see that this conditional probability is the quotient of probability of A and B divided by probability of B. Right? So this is conditional probability of A under the condition that B happens. So it's what fraction of the blue circle is covered by event A and B. And let us recall the definition that events A and B are called independent if the probability of A and B is equal to the product of probability of A times the probability of B. So now let us look at conditional probability in case when events A and B independent, right? So if independent, then the probability of A and B is the product of two probabilities. So we get P of A times P of B divided by P of B, and what we get is P of A. And we get the following conclusion, that if events A and B are independent, then conditional probability of A happening under the condition that B happens is equal to unconditional probability that P of A happens. So this means that effectively this says that the probability of A happening is independent whether B happens or not, right? So the conditional probability is equal to the usual probability of A. And likewise, the same is for B. So the probability of B under the condition of A will be equal to just the regular probability of B. Now, let us look at what happens here. So if our psi is 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. So let us look. What is the conditional probability that Bob observes 0 under the condition that Alice observes 0? Right? So here, if Alice observes 0, then we said that with probability of 100%, Bob will also observe 0. So this is equal to 1. But the regular probability that Bob will observe 0, so is equal to 0.5. So here, Bob will observe 0 with probability 50%. So what we see here is that conditional probability here is not equal to usual probability, unconditional probability. And so this means that these two events are correlated. And the source of this correlation is the entanglement of this state. Now, let us look at the same experiment where we have a pair of photons and one photon being measured by Alice and another photon is measured by Bob. So, but let's look at the case of an unentangled state. So we have unentangled state. So psi is the product, right? So A0 plus B1, tensor product with C0 plus D1, right? So here, for normalization, we have norm of A squared plus norm of B squared is equal to 1, and the same for C and D. Now, so as we wrote before, so this is equal to AC 0, 0 plus AD 0, 1 plus BC 1, 0 plus BD 1, 1. So this tells us the probabilities of observing, so if we have Alice and Bob, so the probability of observing, so there are 4 possible outcomes, right? And so here the probability of observing this outcome is, so here we'll have norm of AC squared. So for 0, 1, this will be norm of AD squared, norm of BC squared, and for 1, 1, this will be norm of BD squared. So these are the probability of each outcome. Now, so what is, let's look, what's the probability that Bob observes 0? So this probability is the sum of the 2 probabilities here. So this is norm of AC squared plus norm of BC squared, right? So this is the same as norm of A squared times norm of C squared plus norm of B squared times norm of C squared. And we can factor here norm of C squared. And so here we get norm of A squared plus norm of B squared. But because of our normalization, this factor is equal to 1. And so what we get is that this is equal to norm of C squared. So the probability that Bob will observe 0 is norm of C squared. Now, let's see. What's the probability that Bob will observe 0 under the condition that Alice also observes 0, right? So now we are restricting our universe only to these 2 cases here, right? And so what we have is, so this is equal to probability that so A is equal to 0 and B is equal to 0 divided by probability that A is equal to 0. Now, the numerator here is equal to AC squared, and denominator, right? So we can see, okay, so we have done this calculation for Bob, but for symmetry, it's clear that if we do the same calculation for Alice, then what we got is norm of A squared, right? So essentially, so what this calculation says is that for unentangled state, if we want to see what's the probability of Bob observing 0, like on his second factor, so this does not depend on the first factor, right? So it doesn't matter what is psi 1. If the state is unentangled, then we can infer the probability of Bob observing 0 just from the second factor. So, right, so it will be norm of C squared. So likewise, the probability of Alice observing 0. So this does not depend on the second factor and only depends on the first factor. And so it's given by norm of A squared. And so we see that the result here is norm of C squared. And so what we obtain is that for unentangled states, we have equality between conditional probability and unconditional probability. Whereas for entangled states, this equality fails, right? So the probability of Bob observing 0 is not equal to probability of Bob observing 0 under the condition that Alice observes 0, right? So here we see a clear difference in results of observations between entangled states and unentangled states. In entangled states, there might be a correlation. For unentangled states, so these two observations are independent, which makes sense physically because unentangled states represent non-interacting particles. So these particles exist just independently of each other and are not talking to each other. And so this means that if we have two independent particles, then when we perform measurements on one particle, these outcomes will be completely independent of the outcomes of measurements of the second particles. But if we have an interacting particle, then their joint state will be entangled. And for interacting particles, we're going to get correlation between measurements of one particle and the outcomes of the measurements of its counterpart. And so this becomes rather counterintuitive, that so can this really be happening, right? So so is there a contradiction with relativity theory here? Because so Alice and Bob can perform their measurements simultaneously, and so this means that there will be some sort of correlation of what happens at the location of Alice, and almost instantaneously. So it will correlate with some event that happens with Bob, right? So if Alice observes 0, right? So there is no prediction what will Alice observe, 0 or 1, just before she makes this measurement, right? So because this is probabilistic event. But once she registers the value of her first bit, immediately, so it tells us something that will happen in a faraway place, right, at the same time, practically. So that it tells that in Bob's location, so Bob is going to register 0 as well. And so this is something that Einstein called spooky action at a distance. So in 1935, so Einstein, Podolsky, and Rosen wrote a paper where they argued that so non-local entanglement should not exist. And so this non-local means spatially separated. So that it should not be possible to obtain the entangled state for two particles that are not together, right? So that one photon flies to the left, another photon flies to the right, and so we have two particles that are far away from each other, yet they are entangled. And so Einstein, Podolsky, and Rosen argued that this should not be happening. And so this was purely on philosophical grounds, so that you should not have this spooky action at a distance, and that the outcome that Alice registers instantaneously transfers to and translates into outcomes that Bob registered. And so this was the rare case when Einstein was proven to be wrong. And so later on, so there were various lab experiments where pairs of entangled photons were generated, and these photons were sent at a distance to each other. And so then this correlation of what happens with Alice and Bob were observed and proved that this entanglement existed even for spatially separated particles. And the ultimate experiment of this kind was performed in, well, 2017. So when China launched a satellite, Micius. And so what they did is, so from the satellite, they would send a pair of photons, an entangled pair of photons, to ground stations in 2 different cities. And so they achieved pairs of entangled photons at a spatial separation of more than 1,000 kilometers. And so they verified entanglement at such a great distance. So this means that this spooky action at a distance seems to exist. And so this does not actually contradict relativity theory, because even though so the outcome at Alice's location happens, well, practically at the same time as the outcome at Bob's location, so this does not allow us to send instantaneously information from Alice's location to Bob's location, because Alice cannot control what the outcome of her experiment is going to be, right? So Alice cannot make this state to be measured to be 0, right? So this is still probabilistic. So there is no way to instantaneously send information from Alice's location to Bob's location using this experiment. Now let us look at entanglement from the point of view of information theory. So suppose we have n-qubit state, which is unentangled. So then this state can be written as a product. So it will be A10 plus B11 tensor ... AN0 plus BN1. Right? Okay, so suppose we want to store this information about this state on, say, a classical computer. So how much memory do we need? Well, to store this unentangled state, we need to store each complex number. So we need to store A1, B1, and so on, AN and BN. So we need to store 2 times n complex numbers. And suppose now we have a general state. So general n-qubit state. And a generic n-qubit state is entangled. So if we write down a random n-qubit, so it will be entangled. And so what we can see here is that if we take the general n-qubit state, then this can be written as the sum k goes from 0 to 2 to the power n minus 1. And so this can be written as ck times k. And so here we see that we need to store two to the power n complex numbers. And so what we see is that in case of quantum systems, the whole is bigger than the sum of its parts. Because what happens here is that for quantum system, the whole is not the sum of its parts, but the whole is the product of its parts, right? So here we have n parts, and each part is two-dimensional, right? So then the dimension of the whole will be the product of 2 times 2 times 2 n times, so it's 2 to the power n. So for classical information, right? So if we have, if we're storing information in a data array, right? So if you double the memory, then you can store double the information. And in quantum states, right? So when we join two quantum systems together, then we don't add capacity, but we multiply capacities of the parts. And because of this, for quantum systems, the whole is much bigger than the sum of the parts, because it's not the sum, but the product.